In this video, we'll talk about an example where y, which is our dependent variable, is binary or is a dummy variable. So we're going to be talking about married women's labor force participation using the MROSE dataset from the Woolrich package. Now, the variable in labor force in LF is equal to 1 if a woman worked for a wage during a certain year and 0 if not. And that's what we're trying to explain. So we will estimate a linear probability model to see the effects of the different types of variables in our data sets on the probability of being in the labor force, right? So this is what we're trying to estimate. So if you want, you can do some exploratory analysis with your data. First, you're going to load your data using the Woolrich package, and then you're going to maybe look at the structure of the data and kind of look at all the different variables you have. So in labor force, notice that this is a 0 or a 1 variable, and we have 22 variables at our disposal, from hours worked to the number of kids that are less than 6 years, or number of kids that are older, between 6 and 18 years of age, the woman's age in years, education, the husband's age and the husband's number of hours worked, stuff like that. All of these variables that define or can influence whether a married woman, ends up in the labor force or not. And this is a data set that's from a published study, and the data set is from 1975. So we're basically going to take a linear model where we are estimating. You're going to do it exactly what you do before. So you're going to estimate a linear model, and you're going to put your dummy variable, the dummy dependent variable, on the left hand side, and you're going to have a bunch of explanatory variables on the right hand side. So here we are taking different variables. So you have this variable called and wife income, which is basically any other income, other sources. So basically, what is the income from other sources? I think that's what it is. Then the education level of the married woman, experience square, age, the number of kids that are young, the number of kids that are older, things like that, right? So we see that mostly all of these are significant. You want to try to go over what these, at least the signs of these variables and whether those make sense. Now let's focus on maybe just one of these variables. Let's say we want to focus on education, the effect of education on whether the married woman is in the labor force or not. And the coefficient here is approximately 3.8%, right? So basically what we can say here is that each year of education increases the probability by an estimated 3.8 percentage points, right? So here I should not say percent because this is not wage on the left hand side, but basically this is, we're measuring the effect of education on the probability. Okay, so this is going to be 3.8 percentage points. And similarly, you can take a look at what are the effects of other variables like experience or having like younger children and other variables. So let's take a look at some of those here. So the effect of having younger kids is negative. The effect of having older kids is positive, but then that's not significant. Okay, but everything else is significant. Okay, so we can also see, what our variables look like specific variables look like. So if you want to look at the kids that are younger, we can see like sort of a frequency table with how many women have 0 children, which is 606 in our sample, and how many women have, let's say, 3 children in our sample, which is only 3 women. Right, so we're seeing that mostly all of the women are concentrated, either they have 0 children or they have 1 child. Now, there are various shortcomings of the linear probability model. However, this is a very useful model to begin with, and it is used a lot in applied economics papers. Let's take a look at the first shortcoming. So one of the most important shortcomings is that the fitted values or the predicted values from an OLS regression using an LPM are never guaranteed to be between 0 and 1. So remember that Y can take a value of 0 or 1, but these fitted values can be sometimes less than 0 or greater than 1, right? And this can be a little embarrassing, but it's not really a big deal, because typically what we're trying to do is we're trying to estimate the partial effects of variables on the outcome that we're measuring, and not really using this model to make predictions. So if we were doing some sort of an exercise where we wanted to make predictions, then this is not a good model to use. But if our goal was to just estimate partial effects, then you can use LPM, no problem. So we can even see this in the data. So, if you've estimated that model before, we can basically construct Y hat. So I'm just going to call it in labor force hat to signify that we're trying to predict this, and use the predict command from the regression that we had stored, right? And then we can sum the values where Y hat is less than 0, and cases where Y hat is greater than 0. So there are 16 cases where the Y hat is actually less than 0, and 17 cases where it's greater than 1. This should be 1. So that's why you want to understand that there are limitations. This is proof that there are limitations to our model. But then if you look at it, in the grand scheme of things, there's only 16 plus 17 values, 33 values out of 753 values that are not in the 0-1 interval. We might also encounter situations where the estimated partial effects are constant throughout the range of the explanatory variables that lead to silly estimated effects for large changes. So in other words, typically the linear probability model does well when your explanatory variables are close to their average values, and does not do well when there are extreme values. So you want, again, remember that, this is again reinforcing the point that linear probability model is good to estimate partial effects and not to make predictions. And you can take a look at, some of the stuff that's written on the slides here. Basically tells you about that same shortcoming. And the third and the last point that I want to make here is that since Y is a dummy or a binary variable, and this has nothing to do with the linear probability model per se, the linear probability model must exhibit heteroskedasticity, except in the case where none of the explanatory variables are affecting the response probability. And this is maybe something a little more advanced, but the idea here is that basically the MLR5 assumption of homoskedasticity can fail, and that can basically make our statistical inference invalid in some cases. Now, we still use the same R squared and adjusted R squared to test goodness of fit. So, I just want you to know that you shouldn't get too hung up on the goodness of it, but just focus on capturing the partial effects that you're interested in when dealing with binary variables. Okay.